Okay, good to go. Anybody else got homework to turn in? Or better yet, does anyone have any questions from the homework? Either one. All right. Which one were you talking? 12. Okay. Garrett, you want yours back too, just in case? All right. Okay. We are, what page? Which one do you have a question? 37. We'll do that one. And let's look at 12 first, since it's the one that people need to turn in. The vectors shown in 335, that's the three vectors A, B, and C, determine B minus 3A, 2A minus 3B plus 2C. Okay, well first let's draw our vectors. We got vector A is 44.0 units. At an angle of 28.0 degrees. B is 26.5 units at an angle of 180 minus 56 is what? 124, you say? minus, yes. If this angle is 56 degrees, that's 124. Okay. So you see what they did there. To get the angle of the standard position, you have to subtract the angle they specified from 180. And then finally we've got vector C is 31.0 units at an angle of 270 degrees. Everybody see that? Starting from here. Okay, that's our three vectors. Get your calculators out. Now we've got to put them each in rectangular notation, or in rectangular form. That means A is going to be 44.0 times the cosine of 28 degrees I plus 44.0 times the sine of 28 degrees J. Which, if we do the arithmetic, somebody do the calculations. What do we get for the horizontal component here? 38.8 or 38.9? No, we'll go with 38.8. And what do we get for the vertical component? .7J. Did anybody get something different for A? All right, B is going to be 26.5 times cosine of 124 I plus 26.5 times the sine of 124 J. Which equals, Tony? What do you get for the horizontal here? Negative 14.8. I. Now what do we get for the vertical component? .0. Now, for C, you don't really have to do a whole lot. And C is 0I minus 31.0J. Everybody see how we can just look at it? There is no horizontal component. It's all in the vertical. Okay, now we need to do what? We need to calculate two sums. B minus 3 times A. Okay, B minus 3 times A. Or put it vertically. That means we've got minus 14.8I plus 22.0J minus, what's A? .38.8I plus 20.7J. All right. You'll notice I put in we're multiplying A times negative 3 times, well, we're multiplying it times 3 and subtracting it. So we're multiplying by negative 3. That gives us, what's 3 times 38.8? .116.4. So minus 116.4I and negative 3 times 20.7. Minus 62.1J. So, ignoring this, we sum these two components together. And we get, what's negative 14.8? Minus 116.4. Negative 131.2I and 22.0 minus 62.1. Minus 40.1J. Now here we only need 3 digits, so that becomes just 131. And that is our vector B minus 3A. Right there. Just for completion's sake, let's go ahead and convert this into polar form, magnitude and direction, like the vectors we started with. If you get it right, but if you don't show me your work. So, how do we get the magnitude of this vector? That's, well, how we'll get the direction. The magnitude of it is (131 squared plus 40.1 squared). You'll notice I'm not worrying about the signs, because when you square a negative, it's still going to be a positive. So for this, I don't really care that they're negatives. And that gives us what? Three digits, you get 137. And the angle theta is the inverse tangent of 40.1 divided by 131. The vertical divided by the horizontal. Again, they're both negatives. So when you divide a negative by a negative, you end up with a positive. What does that give us for an angle? (17.0). Is that correct? Hey, good morning, Deja. Here you go. Yep, that's it. Is this the correct angle? No, they're both negative. And this is one of those times where you have to do the math yourself. Look at our resultant vector. It's minus 131 minus 40. Whereas this tells us we're at 17 degrees going this way. This is one of those times where you have to keep track of where your vector is pointed. So to that 17 degrees, you would add 180 degrees, which would give you a final vector of 137 units at an angle of 197 degrees. Does everybody understand what happened there? Okay. Part 2 was a three-parter, huh? 2 times A minus 3 times B plus 2 times C. Okay. Right again, what is it? What are we doing? 2A. We are doing 12, right? Okay. 2 times A minus 3 times B plus 2 times C. Okay. Let's start by finding 2 times A. 2 times A is 2 times 38.8. I plus 2 times 20.7 J, which equals, what's 2 times 38.8? And 2 times 20.7, 41.4. Okay, so we've got 2 times A is 77.6I plus 41.4J. Now we need 3B. 3 times B is 3 times negative 14.8 I plus 3 times 22.0J. What's 3 times 14.8? Minus 44.4. And 3 times 22? 66? Somebody better make up my mind. Okay, 66J. And now we need 2 times C. Well, 2 times 0, I, is still 0, plus or minus 2 times 31.0 J equals 0I minus 62.0 J. Is that right? Okay. So 2A minus 3B plus 2C. We've got this minus this plus this, so 77.6 minus negative 44.4 equals say again? 122 plus 0 is still 122. All right, now, did someone say they were confused? Where did it? No, seriously, is there something you're not following yet? $122 is this minus this. It's 2A, it's this 2A vector here. I'm taking this minus this plus this. See, this is what we're doing. 2A minus 3B plus 2C. We're subtracting a negative from a positive. Now we're taking 41.4 minus 66.0 gives us what? Negative 24.6 plus negative 62. So subtract 62.0, and that gives us a final negative 86.6J. So that is our resultant vector. 122I minus 86.6J. Now, just to make sure we don't mess up our arithmetic again, let's look at where that vector is. It's plus 122 minus 86.6. It's going to be pointing down here somewhere. What's the magnitude of R? $149.6, so we're going to keep it to 3 digits. That's 150. And theta is the inverse tangent of minus 86.6 divided by 122. Minus 35 degrees. No decimal place? 0.0. Okay. So our resultant vector R in polar form is 150 units at an angle of minus 35 degrees. And you'll notice it is putting us in the right direction. So we don't have to worry about adding 180 degrees to it. Now, any questions about how we did that? It's just basic vector math. Converting from polar to rectangular, doing the scaling, doing the addition and subtraction, and then converting it back to polar. It's tedious. A lot of steps involved. It's not really difficult. You just have to keep a mental picture of what you're doing in your head. All right? Now, what was your one? Yours was from this week's homework. Number 37. And that one's going to work out quite nicely because that's basically what the plan is to do today, is to work some more examples of how you use these kinematic equations to solve problems of motion in 2 dimensions. Oops, sorry. Let's see. I'm sorry, which one did you say? 37. A stunt driver wants to make his car jump over 8 cars parked side by side below a horizontal ramp. With what minimum speed must he drive off the horizontal ramp? The vertical height of the ramp is 1.5 meters above the cars, and the horizontal distance he must clear is 22 meters. Okay. Let's start with our picture. First, it's a horizontal ramp, which means what? His initial velocity is going to be purely horizontal. No vertical component to it. Right? So he will leave with a V naught, which equals V naught I plus 0J, which equals V naught at an angle of 0 degrees. Now, he's got to clear What did it say, 22 meters horizontally? Yeah, 22 meters horizontally. And 1.5 meters vertically. That's the point he has to clear when he leaves and does that. And now we need to know what V sub naught, minimum V sub naught does he have to achieve when he leaves that ramp. So what's the first thing we need to know? We need to know how long he's going to be falling. So, we don't have our kinematic equations written down anywhere, do we? Which of the kinematic equations do we want to use first to find out how long he's going to be falling? Actually, you know, you're right. I mean, there's the one that has x equals x naught plus v sub x t plus a sub 1/2 a sub x t squared. But there's also one that just says v sub y equals v sub y naught plus a sub y times time. Will that one help us? How? We know his initial velocity in the y direction is 0. And we know what the acceleration in the y is, it's just minus g. But we don't know t, and we don't know what his final velocity in the y direction would be. So that gives us 2 unknowns and only 1 equation. So that's not really going to help us. We are going to have to break out see if I can remember how to write this. Y equals y sub naught plus v sub y t minus 1/2 9.8 meters per second squared times time squared. Oh, and that's v sub y naught, right? Yes. Yeah. Okay, well, where do we want to call y equals 0? Up here at the starting point, we'll call this y equals 0. That makes this y equals what? Minus 1.5 meters. We know that, therefore, we can write y sub naught equals 0, v sub naught t equals 0, and that leaves us with minus 1.5 meters is equal to minus 1/2 9.8 meters per second squared times t squared. Well, t squared would give us units of seconds squared, which would cancel the per second squared in g, leaving us with meters equals meters. So, minus 1.5 meters equals minus 9.8 divided by 2 is, what was it again? 4.9 meters per second squared times t squared. If we divide both sides by minus 4.9, what do we get? (0.31 seconds squared equals t squared. Well, at that point, it's just a matter of taking the square root of both sides, which gives us and by the way, is anybody getting different numbers from doing the calculations? If you do, speak up, because we divided both sides by, we divided negative 1.5 by negative 4.9. Yeah, and it's negative 1.5 meters divided by negative 4.9 meters per second squared, which means we end up with meters dividing out, canceling out, and the second squared coming back up into the numerator. So we end up with 0.31 seconds squared equals t squared, and what's the square root of 0.31? 0.57. That means he's going to be falling for about half a second. Means a whole lot of people spend a whole lot of money to watch something that don't last but for about half a second. So, okay, we know how long he's going to be in the air before he falls that far, and we know how far he needs to travel horizontally before he does. Right? So, he needs to travel 22 meters at some velocity meters per second times 0.57 seconds. If we divide 22.0 meters by 0.57 seconds, what does that give us for V sub naught? .6 meters per second. Of course, we didn't keep but two significant digits here. So we really should round that to 39 meters per second. But either way, that is part A. Now, for part B, instead of having a horizontal takeoff, we're going to have the ramp tilted upwards at 7 degrees. So, this time, sorry, it said 7.0 degrees. Okay. We're still going to assume that the top of the ramp is y equals 0. and that the distance he has to travel is 22 meters. That's where he has to clear, but now that's his trajectory. That means his V naught is at an angle of 7 degrees, which means it's V naught times cosine of 7 I plus V naught times sine of 7 J. We still need to figure out how long he's going to be in the air. How do we figure out how long he's going to be in the air? We've still got our same equation. Y equals y sub naught plus v sub naught y times time minus 4.9 meters per second squared times time squared. That's still true. Does anyone have trouble with me going ahead and dividing 9.8 by 2 right up front? Okay. Everybody understands how that became 4.9. Well, y sub naught is still 0. Y is still minus 1.5 meters. But now we've got this extra pesky term here, v sub naught y times time minus 4.9 meters per second squared times time squared. Who wants to take a guess at how we proceed from here? What, V naught sub y? Well, that's just V naught times sine of 7 degrees. If we get V naught, we can get V naught y, but we don't know what V naught is yet. What we have to figure out is how long is he going to be in the air. And it's not going to still be a half a second. See, he's not starting off at 0. He's got a positive velocity component. That sounds like a good place to start. Let's go down that rabbit hole and see if we find a way out the other end. How's that? All right. Let's put this in order to use the quadratic equation, the first thing we have to do is put it in standard form, which is 0 equals what? Negative 4.9 t squared v sub naught y times t plus 1.5 meters. Very good. And the quadratic equation then tells us t equals negative b, which is minus v sub naught y, plus or minus the square root of v sub naught y squared minus 4 times negative 4.9 times 1.5. That's 4 times a times c, all divided by 2 times minus 4.9, which is minus 9.8. And we have an unknown under this radical. We seem to be at an impasse, don't we? Anybody got any ideas? Look at our kinematic equations again. See if there's anything there that looks like it might help us. Something we can solve for to find out basically, what do we have here? We have two unknowns. We don't know time, and we don't know velocity. What does that mean we have to have? If we're solving for two unknowns, what do we have to have? We have to have two independent equations that we solve simultaneously. So, we've got all of these different kinematic equations in y, but are they actually that independent? They're kind of all derived from the same thing, but we do have two very independent axes that we're dealing with here. So anything in x is going to be independent of what we do in y, correct? So how could we, what if we take and look at how long it's going to take him to travel 22 meters? Then we have what? X equals 22 meters will be equal to x sub naught, which we're going to call this x equals 0. Plus v sub naught x times time plus 1/2 a sub x times time squared. Right? Now, does everybody see that this is a completely independent equation from this one? Well, we still have two unknown variables in it, but and in point of fact, this one is a different unknown variable than this one. But we can always write both of them in terms of v sub naught times the sine or times the trig function of a known angle. So we can express both v sub naught x and v sub naught y, both as simply v sub naught times this cosine or sine of 7 degrees. So so even though they look like two different unknown variables in these two different equations, we can write them as a single. Let's we know that there is no acceleration in x once he leaves the ramp. There's nothing. And this is 0. So we basically got 22 meters is equal to v sub naught x times time, which we can write as v sub naught times the cosine of 7 degrees times time. And that's 22 meters. We've also got, what do we have here? Minus 1.5 meters is equal to v sub naught y, which is v sub naught times the sine of 7 degrees times t minus 4.9 meters per second squared times t squared. Now let me straighten this up. How would we go about solving two equations and two unknowns here? Well, we can start by making them a little more, make them look a little better. 0 equals minus 22.0 meters plus v sub naught cosine 7 times time. And 0 is also equal to 1.5 meters plus v sub naught sine 7 degrees times time minus 4.9 meters per second squared times time squared. How can we make those trigonometric functions go away? We're running out of class time real quick, aren't we? No, that's okay. This looks like it's a good exercise for y'all to ponder. What we have right here, two independent equations with two unknowns, V naught and T. How many, have y'all, show of hands, how many of you have solved simultaneous equations like this before? Two equations and two unknowns, three equations and three unknowns? No. Okay. Well, this might be a little more involved than I was expecting. Okay. We're not going to rush through it in 2 minutes, so I'm not going to. I'll leave y'all with this one to ponder till Friday. Generally, what you need to do is you need to add them together and make in such a way that one of the unknowns can be written in terms of the other. Basically, if we could solve this, if we could say solve v sub naught as a function of t, then we could replace it. But we'll pick this one up on Friday. We have lab tomorrow. Tomorrow we're going to be doing projectile motion. We're in lab, so we're going to start empirically observing that we can actually do these calculations and they are meaningful and accurate. Anybody else want to turn in homework?